All right, so we are going to talk about conservation of momentum and how it can be applied to collisions today. So our topic for our notes, again, I encourage you all to make sure that you are copying these down. These are outline notes, so make sure you copy those down and add any additional notes based off of what I say in this video if they're helpful to you. So our topic today is the conservation of momentum and collisions. Your objective is to be able to describe the law of conservation of momentum and apply its principles to describe collisions. So the essential question that you are trying to answer in your summary at the end of your notes today is what happens in a collision? What types of collisions are there? What is happening to the objects involved in a collision based off of what you know about momentum and the conservation of momentum. So let's first talk about the law of conservation of momentum. Now we know from our physics classes that a scientific law describes the way it's a rule that nature must obey. It basically describes this is the way things are. There is not much we can change about it. Again, scientific laws are based off of millions and millions of experiments and observations. So the law of conservation of momentum states that the total momentum in a system remains constant. Now, I do want to direct your attention to what a system is defined as. Oops, and I used the wrong marker here. So a system is defined as a collection of physical objects chosen for study. So a system would include multiple scenarios, but we're really focusing on a couple of objects, a specific part of a universe at a given time to our study. So in this example, maybe we have a comet in our solar system, and it has a certain momentum, right? It has a mass and it has a velocity. So we'll label that mass 1 and then velocity, and we'll say that that's our initial velocity. So again, I'm just using these variables to describe what's going on in the system. You all are probably pretty familiar with what collisions look like in real life to begin with. But I did want to point your attention to that. So again, keep in mind, mass times velocity is equal to momentum. So we got m1 v1I. Again, that stands for, this is the velocity of the first object, and it is the initial velocity. So that's our momentum 1, right? Say this comet breaks in two. Now we have two masses. We've got mass 2 and mass 3. Each one is also going to have its own velocity. So we'll say V2, and I'll call that the final velocity because we're kind of fast forwarding in time. And then this one is going to be V3, final velocity. So now we have a momentum over on this side in this new scenario of M2, V2, V2 final, right? That's talking about this comet right here. And we have another comet, which is this comet right here. It's a smaller comet from the bigger comet that broke in two. So that comet would be its mass 3 times its velocity. So what this is saying is, and then this would be our second momentum. What this is saying is that momentum 1, which is P1, right? That's momentum 1, is equal to momentum 2. That's our law of conservation of momentum. So even though this larger comet broke up into two smaller comets, what the law of conservation of momentum says is that even though there's a change in mass, even though there's a change in velocity, the total momentum in this system, in this specific object that we are dealing with right now, even though it breaks up into two, that total momentum is going to remain the same. So the law of conservation of momentum is very helpful for us when we are looking at collisions. So let's quickly define what a collision is. Now, a collision is an event where two or more objects exert a force on each other in a short period of time. Again, you all are probably familiar with what a collision looks like. You see collisions in everyday life. So let's define specifically a couple different types of collisions that we study in physics. The first type of collision is called an elastic collision. So objects involved in the collision remain separate and the total kinetic energy is conserved, meaning we will talk about energy soon enough, but what I want y'all to take away is that these objects are not stopping and they are not losing any of their moving energy that they start off with. So say we have two pairs of marbles, and we're going off of this drawing right here now. So say we have two pairs of marbles. We've got marble 1 with a mass 1. Again, I'm using these little subscripts, these tiny numbers behind behind these variables to distinguish which one is which. So again, we've got multiple masses in this scenario. So I need to distinguish, okay, the red is going to be mass 1, the green is going to be mass 2. So again, we've got one red marble with a certain mass. It is traveling with a certain velocity, which we label as V1. And this is its initial velocity. And the same goes for the green marble. It's got its own mass. It is traveling at a specific velocity, which we label V2. And again, this is its initial velocity. So these two are traveling toward each other, getting ready to collide. Now, here's where we have the collision. So say they collide. Now you find them traveling in the opposite directions after they collide. So now marble 1 has a new final velocity, which we represent here. And marble 2, its mass is still the same, but it has a new final velocity as well. So all of this is meant to say that the momentum is conserved. So even though we've got these tiny little subscripts here, what this is really saying is there is a momentum here, which is represented by mv. And again, that is a momentum. And how about we label this momentum 1, initial. Our initial momentum of marble 1 plus our initial momentum of marble 2 is equal to our final momentum of marble 1. Oop, and I just wrote the wrong letter there. Plus our final momentum of marble 2. And I'm going to write momentum is conserved. So that's an elastic collision. These collisions are really easy to work with, but they don't actually happen that much in nature. Typically, some energy is lost during collisions. That's why you hear the smack of the marbles when they come together and collide. So that energy might be lost to heat, it might be lost to sound, it might be lost to friction. So that's what we call nearly elastic collisions. And nearly elastic collisions we tend to, in the physics classroom, just describe as elastic collisions. We know in real life that it is not perfectly elastic, but we are going to estimate that it is perfectly elastic. Okay, so we've talked about elastic collisions. Now let's talk about inelastic collisions. So an inelastic collision describes a collision where the objects become one mass. And typically they're going to lose some of their kinetic energy. So think of like a car crash. So I'll use cars in this example. We have car 1, which is hurtling toward car 2. So car 1 is in red. It has a mass of 1 and it has a initial velocity, right? And it's hurtling toward car 2, which also has its own mass. Let's say its initial velocity is 0. So let's say that car 2 is not moving and car 1 is hurtling toward it at a very fast velocity. So car 1, and I'm going to write, here's our collision represented by this after the collision. So car 1 collides with car 2, and then they actually stick together and start moving together after they collide. So now we have this phenomenon where they have a mass, which is both of their masses added together. So what perfectly inelastic collisions are saying is that we have a momentum here. So we'll say that's P1 initial plus our P2 initial becomes basically P1 plus P2. That's our, well, let me rewrite this. So car 1's initial momentum, then we've got car 2's initial momentum, is going to equal the final momentum of this entire system, the two cars and their final velocity at which they travel. So again, momentum is still conserved, even though they're going slower. The law of conservation of momentum states that even in an inelastic collision, momentum is still conserved. The only thing that is not conserved is kinetic energy. So I hope this helps. And again, this is a cool topic describing some things that you all have learned about momentum and how those can apply to collisions and real life scenarios. So again, do not forget to write your 1 to 2 sentence summary, and I look forward to discussing this with you all in class.